Hi, welcome to this presentation on the Polaris Framework for creating and enforcing complex service level objectives. My name is Thomas Postai, and together with my colleague Philipp Reit, I'm going to present our framework to you. So to get started, let's briefly talk about what SLAs and SLOs are. So service level agreements are well known from cloud computing. They define the bounds within which a service has to operate, like for example 99.9% uptime. An SLA consists of one or more service level objectives, or SLOs, where an SLO is a commitment to maintain a particular state of the service in a given period. And that means SLOs are the measurable parts of SLAs. But today, SLOs are often limited to simple capacity guarantees, such as CPU usage, RAM usage, or response time. However, high-level SLOs, such as the efficiency of a service, would be much more suitable as business key performance indicators. And this is what we want to realize with the Polaris framework. So let's take a look at how SLOs work in general. On a conceptual level, we always start out with one or more metrics that are read from the system, from your deployment, and they go into the service level objective. The SLO evaluates if it is currently fulfilled or violated, and if it is violated, it triggers what we call an elasticity strategy to bring the workload back into the state where it fulfills the SLO. So this can be, for example, horizontal scaling, so creating more replicas or reducing the number of replicas. What's commonly seen in production use today is that we have rather simple metrics such as CPU usage or memory usage. And the SLOs are also usually very simple, like, for example, the average of a certain value, like, for example, the CPU usage across all your instances. And then the SLOs are often tightly coupled with a specific elasticity strategy. Like, for example, in the very popular Kubernetes horizontal pod autoscaler, it's horizontal scaling. So you have an average SLO that's tied to horizontal scaling. HPA does allow you to use custom metrics as well, and also modify this average part here a little bit, but using custom metrics requires you to deploy a distinct Kubernetes API server which serves these custom metrics, so that's additional deployment and maintenance overhead. And with Polaris, we want to simplify things. So in Polaris, we have decided to remove this tight coupling between the SLO and the elasticity strategy. So if we stay with the CPU usage example, we have the CPU usage metric that goes into an average CPU SLO, but this is only very loosely coupled to the horizontal elasticity strategy, which gives us the flexibility that we can easily replace the horizontal scaling, for example, with vertical scaling or with a completely customized elasticity strategy that fits our specific workload type. Or it also allows us to use a completely different SLO, like a high-level efficiency SLO, and mix and match that with multiple elasticity strategies. And of course, we can also use other metrics for our SLOs very easily. So we have seen that the evaluation of an SLO involves one or more metrics, the SLO itself, and an elasticity strategy. And Polaris is a framework for building and customizing all these three components in TypeScript. It features decoupling of SLOs from elasticity strategies and just loosely links them through what we call an SLO mapping. We will get into further details on that a little bit later. And this approach increases the number of possible SLO and elasticity strategy combinations. Now, in the next few minutes, we will take a brief look at how each of these components up here can be realized with Polaris. Let's start with the metrics. Now, like other frameworks, Polaris, of course, supports low-level metrics such as CPU usage, memory usage, and so on. But we also support high-level metrics because high-level SLOs require high-level metrics, which are not directly observable on the system. So we have this feature called composed metrics, and the composed metric is an aggregation of multiple lower-level metrics. They're often computed by a distinct external controller, so they're not integrated into the SLO controller itself to keep things more flexible. And we share them through what we call a metric store. Now, currently we use Prometheus as a metric store, but in theory, you could use any time series database for that. And very important, a composed metric can also be a prediction of the future values of another metric. So this allows you to actually do proactive scaling. So let's take a brief look at how composed metrics work. So let's say we have an efficiency SLO controller that is supposed to evaluate the resource efficiency of our deployment. So in its control loop, it gets the efficiency of the target workload, so the workload to which the SLO has been applied. And to expose that metric, we have an abstraction called the metric source. Now the metric source goes to the metric store and reads the efficiency of the target workload from there. As you can see, the metric store, in this case Prometheus, stores raw metrics, but also the composed metrics. So how do these composed metrics get in there? We have a resource efficiency controller that periodically queries the low-level metrics like RAM, CPU, memory, and so on, and combines them with the total cost of the target to compute the overall efficiency. Now, the total cost is another composed metric because it is actually composed of the sum of costs, like, for example, the number of nodes you're using, the number of storage volumes you're using, and so on. So the total cost is again obtained through a metric source, which queries the metric store. And we have another controller that actually computes the total cost and writes it to the metric store. And after combining various low-level metrics with the total cost, the efficiency resource controller then writes the target workload's efficiency to the composed as a composed metric to the metric store, so that the SLO controller can retrieve it and evaluate it. As previously mentioned, we don't only support reactive metrics, but also predictive metrics to add support for proactive scaling. Now, in this case, we use a polyglot approach that combines some TypeScript code and Python code. Why? Because from the Polaris side, the users expect the TypeScript code to customize their controllers and their SLOs, and AI developers are usually more familiar with Python, so each can focus on their strengths. In order to enable our predictive controllers, we have developed and trained two deep learning models. We have one long short-term memory, LSTM, deep learning model, which is a classic architecture for time series data. And we also have a transformer deep learning model. Now, transformers have been very successfully used on natural language processing, and they're now increasingly being adopted by other fields as well. Both models are trained to forecast the high-level efficiency metric given low-level cluster metrics. So with the metrics ready and in place, let's move on to the SLOs. An SLO is evaluated by an SLO controller. The SLO controller periodically evaluates all its input metrics to check if the SLO is currently fulfilled or violated. And if it is violated, then it triggers a user-configured elasticity strategy. Now with Polaris, SLO controllers are very easily buildable because our framework actually comes with a full implementation of the evaluation loop and automatic triggering of the elasticity strategy. So you don't need to worry about any of this. You really only need to implement your business logic. And in fact, if you want to implement the efficiency SLO that I mentioned previously, the code on the right here is actually all you would need to write. So read the metric and then compute an SLO compliance value based on the metric. So if the SLO is violated, it needs to trigger an elasticity strategy. An elasticity strategy will modify workload's resources, its instances, or the configuration or a combination of them in response to an SLO violation. Out of the box, Polaris comes with horizontal scaling and vertical scaling as elasticity strategies, but we make it easy for you to build your own custom elasticity strategies, either for a specific workload or a generic elasticity strategy. For example, if you just want to customize the horizontal elasticity strategy with a different formula, for example, for computing the new number of replicas, the code on the right is all you would need to write, because you can extend the existing horizontal or vertical controller. So now that we have all controller types ready, how do we apply the SLO to our target deployment? So this is something that we're using the SLO mapping for. The SLO mapping creates the association between the SLO itself, including all configuration, like for example thresholds, the target deployment, and the elasticity strategy. And the SLO mapping gives us the flexibility that if we want to change one of these components, like for example the elasticity strategy, we can only just change the configuration in the SLO mapping here, but we don't need to touch the SLO or the target deployment. Another one of Polaris' features is type safety. Because you can specify your SLO mappings in TypeScript, you also get all the type safety features of that. So based on your SLO, you have a certain type for configuration, and it produces a certain output type, and this determines which elasticity strategies you can use. So in general, the SLO output type is what determines if an SLO is compatible with an elasticity strategy or not. We provide a generic SLO output type called SLO compliance, which we of course recommend you to use for maximum compatibility. But if your SLO needs to produce a special type of output and you want to create a special elasticity strategy for that, you can of course do that. So all this sounds great, but you might be asking yourself, how much effort is it to set up a Polaris project and to create one of these controllers? Now, the effort is very little because we provide a command line interface, a CLI, which service providers, developers, and consumers of Polaris can use to create and manage their controllers and SLOs. So the CLI allows you to create and generate composed metric types and controllers for that, SLO mappings and controllers, elasticity strategies and controllers, and also generate SLO mapping instances and configure them. Now this allows for a lower entrance barrier for new developers, and since the Polaris CLI is based on the NX CLI, which is a very popular command line interface for TypeScript monorepositories, this actually allows you to combine Polaris-based components with other projects in your monorepository. And now I'm going to hand over to my colleague Philip, who's going to talk about proactive scaling.
After showing the various parts from the Polaris framework, we now turn over to the support for proactive scaling. We will first discuss the differences between reactive and proactive, as well as the integration into Polaris. Imagine you have deployed a SLO controller that scales the system based on efficiency. We are using the composed metric controller that is exposed to the metric store, in our case Prometheus, and calculates the efficiency based on the current usage. The scaling is therefore reactive. On the other hand, if you deploy a predicted metric controller, we automatically use a proactive scaling system, because the predicted metric controller uses an integrated AI service to predict future efficiency based on the current usage. The two controllers are easily interchangeable through the Polaris CLI. To fully understand the solution, we want to highlight challenges we focused on when developing the predicted metric controller. In general, we have in this domain two types of participants. On the one side, we have the Polaris users, which are responsible for creating and deploying components similar to the composed metric controller. It's not their responsibility to calculate the value, but their goal is to provide the SLO controller with some value. On the other side, we have the AI developers that are not familiar with any orchestration services and want to focus on the prediction. Therefore, we have developed a Python-based connector for integrating AI and ML models. Additionally, the solution should be future-proof with regards to the MLOps movement and should support automatic rollouts for model updates. Based on these two participant types, we have developed the predicted metric controller. It consists of two containers, a composed metric controller and the AI proxy. The composed metric controller calls the AI proxy whenever the metric store, for example Prometheus, scraps it and maps the response, the AI prediction, to a composed metric type. The AI proxy is Python based and executes the following steps after being invoked via REST. It queries the raw metrics from the metric store, then builds the input features, and afterwards calls the AI service. The AI proxy is Python based and executes the following steps after being invoked via REST. It queries the raw metrics from the metric store, then builds the input features, and afterwards calls the AI service. AI developers can specify in the configuration file which metrics to fetch from the metric store. Currently, we only support Prometheus, but this can be easily extended. The only implementation that has to be done is the problem-specific preprocessing. Afterwards, the proxy calls the AI service, for example TensorFlow serving, which we support out of the box, and then the response returns back to the composed metric controller and can be sent to the metric store. This solution helps the participants to focus solely on their strengths while building a coherent deployment unit that is easy to use and supports automatic model updates.